So I'm with the Nfdi4CAT at TU Dortmund. You will hear an additional presentation from Mark Dörr tomorrow on more biocatalysis focused topics. I will discuss a little bit about more the heterogeneous and homogeneously catalyzed reactions. And since we are quite a multi-domain topic, you will see some unique challenges at Nfdi4CAT, which I think no other NFDI is facing right now. And before I go into how we try to solve some of these, I first want to give you a slight impression on how does the typical workflow, or how does typical people and mindsets in catalysis work. So we can, to start, we can differentiate. Sorry, can you hear me? Mark? Is the audio scattered or just Mark?
It's just Mark. We can hear you perfectly fine.
Okay.
Yep.
We can differentiate in catalysis a little bit into practitioner and theoretician, the ones generating data and the ones mostly analyzing it, doing simulations. We heavily rely on simulations in many fields because it's quite difficult to describe all the effects occurring at once in catalysis. So if we look at a practitioner, we can often see that they perform multiple measurements over their span. Typically, PhD student, for example, has one topic to work on. He performs multiple measurements to describe a single phenomena. He is seeing, he had the task of investigating, and a lot of the data which is generated focuses just on describing this interpretation. And it's often just interpreted in publications rather than is really well described in the data sets itself, especially since they are most often not connected. While the theoretician often has to analyze this very heterogeneous data for phenomena hardly to describe, like the kinetics effect on the surface of a heterogeneous catalyst. And so they often also work as practitioners because they need to validate a lot of stuff. What is critical here is that practitioners often leave out data because they simply say, okay, this is obvious. Everybody in our field knows what we are seeing here in this data set. But we often see the challenge that if you try to simulate it, then we need this data to validate really that we are heterogeneous in the assumptions we are making. But this all is due to some problems we are facing because we typically have the complexity in the setup. So every measurement, every setup is typically quite unique. Every university builds their own pilot plants. Sometimes even PhD students build their own example reactor, which is not digitized well enough. So many information are just collected in Excel files and so on. And practitioners are often a jack of all trades, but a master of none. So if they work, for example, in biocatalysis, they might need to find out how to 3D print their own surface on which they want to immobilize enzymes just to perform operando catalysis and analyze an IR spectrum. So it's really quite diverse what they need to know. And our models are complex as well by having very little to be describable and a lot of complexities all working simultaneously. So that's why I want to show you what a typical use case, for example, could look like. We generally have like 3 to 4 steps: catalyst preparation, then some processing, which is done to get the reactions, and then afterwards analysis, sometimes done operando, so directly in or parallel to the process, but sometimes also later after the process. For the catalyst preparation, we often do not perform one catalyst preparation, but multiple, have some formulation done in Erlenmeyer flasks and so on, do some treatments like baking them in the oven, reducing them, and so on. But most of this information is not necessarily recorded, because if it works, it works. Then we have some reaction process, which can be performed in quite complex constructs with recycles and so on. Everybody builds their own setup, like I said. We might even have dynamic time set series, operando measurements, and so on. And what we typically get out is like a multidimensional time series data, as you can see here, which is basically the deactivation characterization of one catalyst, where multiple chemical selectivities are shown over changing temperatures, pressure, compositions, volume flows. So we could say like one data set can have up to 40 parameters with, and if we reduce the complexity here, but if we try to show all parameters, it's quite complex. So describing this data is also quite complex. What's the challenge here is that we have data separated into multiple files. Like I try to present, we first have catalyst preparation, which has some raw metadata, raw data files for analyzing, for example, the topology of a catalyst, a process description, and then several metadata files. But we cannot, if we truly want to evaluate them, separate them from each other, because the provenance of data is quite important. The uniqueness of the process often means that we have the uniqueness in the data model, which also poses quite a challenge. But as we often see, catalysis handles scarcity of data and information quite well. So even from little to no data, we can often interpolate, assume, and get a process running, validate it ourselves, and go on. The question mainly arises, so how do we face this overall challenge of working here with metadata, cross-connecting it, and so on and so forth? What we saw in our Nfdi4CAT is that we need to, of course, face the challenge of having multiple data sets. So what we try to do is to get a pipeline where we can first annotate data with, for example, general purpose semantics like the Nfdi4CAT, build data models to enrich and have consistent modeling syntaxes so that the uniqueness is not as harsh as shown previously, which then at least gives a partial structure to the data so that we can later on combine it into ontologies. We are developing our own ontologies, but we are also heavily relying on existing OBO ontologies to work to describe our data we are seeing and generating. We have many tools, and like I said, we are looking at data which is stored and saved on different archives. We are estimating that the connected data is not just at our repositories, but for example, stored in data repositories like Nomad you've seen yesterday or Chemotion for some analysis types. And so we have ontologies, we have developed tools for extending these ontologies. We have a whole collection of ontologies and how valuable they are for certain aspects and domains, so that you can also like build your own application ontology. We try to heavily rely on data models so that we at least have a general structure in our raw data. We try to give semantics and also have our own PID service for cross-connecting information. But now, since I showed you how this world looks like and what we face, I want to get over to the ontology aspects. And like I said, there is a lot of stuff not modeled in ontologies, and we need to classify and structure and harvest a lot of the hidden knowledges. So we started with some competency question on what's important for ontologists, like why do I get a side product, which substances is being catalyzed in my mixture, do I have the right reaction conditions for this reaction, and started to look at the typical model of a reaction and said, like, can we depict it also in an ontology? And yes, we found out it's possible. We say, like, we have an initial mixture, we have some reaction products, these can be measured, a reaction is happening somewhere here, and a catalyst is acting on it. But what we see here is a reaction and a catalyst is quite an implicit concept. We cannot plan what is catalyzing which reaction and when which reaction occurs. We do know something, but in general, we need to classify it by what happens inside the reaction. And therefore, the question comes, how can we classify the representation of implicit concepts with open world logic, which is not quite easy? Or how do we classify reaction experiments based on unasserted reaction types, so not given by the data set, which are obviously occurring, like I explained, a catalyst, a practitioner often leaves out the data. So we try to set our Nfdi4CAT ontology inside the domain of different ontologies because we don't want to reinvent the wheel. We try to handle a lot of stuff with a Python pipeline because setting up new ontologies and so on is quite complex, and you will see the logic in a few seconds, which we also implemented via a Python API, which is shown here, where we try to use a slightly different kind of approach, where we used basically the logic typically with subclass of the different way around. So in Protégé, it's often called general class axioms, where you say, like, if every conditions are met, then you can classify an experiment which has certain chemicals as a certain reaction. This is sadly quite computationally expensive. Nonetheless, I wanted to show you how this model looks like. So first of all, we could model a data set by describing an experiment, like here a reaction experiment with some educts, some products, some setup. We can have some reference data, like what is a Haber-Bosch reaction, what is a methanation reaction, what are their catalytic properties. And if we implement the logic right, we can get an automatic classification that a reaction is having a certain idealized reaction occurring inside of the experiment, and that certain materials have catalytic properties regarding this reaction. Okay, like I said, the OVL approach is having some problems. So what we saw is that we might want to switch and get to some better approach. And where I stumbled upon was that there are new developments in the realm of Shackle, especially in the world of Shackle advanced features. Who knows Shackle and has done a lot of Shackle knows that you can also define an ontology in Shackle terminology. But what you can do with Shackle advanced features is basically implement SparkQL queries as hard logic into a shape. And therefore it can, for example, construct based on a Sparkle query you placed in a Shackle shape, and therefore your logic is a permanent artifact similar to what your OWL logic is, and you can import it parallel to your OWL logic and use it. So we are currently on a step where we try to implement the whole terminology in OWL and do most of the classifying and inferencing based on SparkQL queries, which has many benefits. like that we can handle algebra and calculus, like is it in the right temperature range, is it in the right pressure range, are all the conditions mathematically established, and yeah, it's working quite well. The problem now just arises on how to model this. For OVL, this was quite easy. We needed to implement it all as model instances. For Jekyll Advanced Feature, we can do much more, but we need to have ontologies which also work well. And so I just want to show you one example of how difficult it can be to, even if we know that this Jekyll approach works, classify a reaction. The aspect here is that we want to, for example, model a Mannich reaction, which we want to model by functional groups, as you can see by the substitute groups here. And we don't want to reinvent the wheel. So we want to reuse a lot of stuff because we are multi-domain, having a multi-domain approach, and we really need to stay with the logic. Yeah, but then we soon arise to the challenge of how does CABI represent chemical substances and how do we represent chemical substances. So for example, an acetone batch, do we want to describe has part acetone? Acetone is a class in CABI, which would lead to logical inconsistencies if we run a reasoner. Of course, there are other data models, but where are they described? Where can I find them? How do I tell somebody who's not interested in doing too much work in semantics on describing this in the correct way? Nice question. How do we describe technical mixtures and complex structures like iron catalysts? We have certain terminology like primarily composed of, but iron might be just the least amount of the catalyst. So should we say like pentarily composed of, and what's then even the most important component? How do we describe technical chemicals if we get them out of a plant who is not producing at super purity or something like that? How do we get PubChem instances into the CABI and so on? There are a lot of questions. But there are not only questions in CABI, but also, for example, in RxNO. If you look at the definition of RxNO, I've given it here, and a contrary definition from Wikipedia. You can see that ammonia or amines react with a non-analyzable aldehyde, often methanol, to an analyzable and an analyzable carbonyl to a beta-amino compound. What's the essence of the Wikipedia definition is, first of all, the analyzable aldehyde is well. Wikipedia doesn't do it in the same way. They just say formaldehyde, but RxNO doesn't look at N-Mannich reaction where there is where two nitrogen compounds are reacting. So the analyzable carbonyl is changed, for example, by a nitrile. And so we cannot model, we need to add some stuff into the RxNO, for example, here to clean it up. There are also some other aspects, like not everything is modeled. If you see here in the right side, we, for example, only have the analyzable carbonyl compound as has specified reactant, so only one of the three. But what is even more confusing, every reaction and every named reaction is some planned synthesis. Why? Reactions might occur as side reactions, and thus they were never planned. And still we want to describe them. So there are some definitions which also need to be changed. Yes, to finish off, Nfdi4CAT heavily relies on other modeling approaches, other ontologies to cross-connect many of the domains. And so we really hope that we get some clarification in aspects like the CABI, so that we also have an easier time of modeling information in the right way and cross-connecting from ontology to ontology. Yeah, thank you. And questions?